Hello students, welcome to yet another session of electronics. This is our third session of this week. We will continue to discuss principles of electricity. Up till now we talked about Ohm's law, Kirchhoff's laws, which are used for simplifying the circuits to find branch currents. Okay, so you also know now what is a branch and what is a node and what is a loop, what is a mesh. So these are all important terminologies which we are going to use. So according to Ohm's law, it says that the statement of Ohm's law goes like this: current through the conductor is directly proportional to potential difference across its ends, provided physical conditions are constant. So it says V is equal to I into R. This is the equation of Ohm's law. It can be expressed in different ways. This we have seen. We are going to use this extensively. But Ohm's law is not sufficient for complicated circuits. So we went ahead with Kirchhoff's laws. There are Kirchhoff's current law and Kirchhoff's voltage law. Kirchhoff's current law is to do with a node or a junction. At a junction, several currents meet. So according to Kirchhoff's law, sum of currents entering the node is equal to sum of currents leaving the node. So in this case, particular example, two currents are entering, two currents are leaving. So we can say that I1 plus I2, which are entering, is equal to I3 plus I4. So that is how you write expressions for currents using Kirchhoff's current law. Now the Kirchhoff's voltage law is to do with the loop or a mesh where a closed circuit is there, which consists of resistors and EMFs. It can be more number of EMFs also, or there may not be any EMFs also. Only resistors can also be there. So if there is any closed loop, you can apply Kirchhoff's voltage law. According to Kirchhoff's voltage law, sum of EMFs in a loop is equal to sum of IR drops. IR is nothing but, see here, Ohm's law. IR is nothing but V. So when you have current flowing in a branch, the drop across resistance will be I into R1. The drop across this resistance is going to be I into R2. So I into R1 is nothing but V1, I into R2 is nothing but V2 according to Ohm's law. So Kirchhoff's voltage law says that the sum of EMFs is equal to sum of voltage drops. So in this particular example, we have only one EMF. So V is equal to the drops. These are the two drops. So V1 plus V2. Or what is V1? V1 is nothing but I into R1. And V2 is nothing but I into R2. So that is the expression over here. See, sum of EMFs is equal to sum of IR drops, or V is equal to IR1 plus IR2. So V is equal to V1 plus V2. So we are going to use all of these now to solve problems. You have to be good in solving problems. Again, this is there for your second PUC physics also. If you're good at it, you will score really well there also. So please pay more attention and learn. You can go back and see also for clarity of understanding. So even before we start solving problems, you need to know certain sign conventions that we use to solve the problems. So here it goes: sign conventions for IR drops and battery EMFs. So for example, EMF's polarity remains the same. You cannot change. Smaller line is always negative, bigger line is always positive. And the current flows from positive to negative. We know that. Okay. If the direction of loop current is in the same direction of conventional direction of flow, then we will take EMF as positive. Okay. When you see the problem, you will understand better. So remember, loop current direction and conventional direction current of EMF is the same, then we will take EMF as positive. If it is other way around, if the direction of loop current is like this and the EMF direction is like this, then we will take it as negative. Similarly, for IR drops also, if the conventional direction of current is same as direction of loop current, we will take IR drop as positive. If other way around, then we will take it as negative. How to see it in a problem? We will take an example. Let us take an example which consists of two EMFs and two resistors. So essentially we have two EMFs, two IR drops. So how to consider the polarity while writing the equation? For the loop we have to use KVL, right? So the loop current we are considering is like this. The loop current keeps on flowing in the loop like this. So when the loop current is flowing through this EMF E1, both are in the same direction. See, conventional direction also goes from positive to negative, and loop current is also in the same direction. So we will take E1 as positive. That is the first one. Continue with the R1 now. When you pass the loop current through R1 like this, conventional direction also is in the same direction. See, I is flowing in the same direction as loop current. So we will take IR1 drop as positive. So IR1 drop is positive. Continue the loop current further down. You have E2. And E2 is having positive here, negative here. And it is opposite. Isn't it? It is opposite to the EMF sign. That is why E2 becomes negative. Whereas when you come down here, conventional direction is same as the loop current flowing through the resistor R2. So IR2 drop is also positive. So how to write equation? Sum of EMFs is equal to sum of IR drops according to KVL. So E1 is positive, E2 is negative. So E1 minus E2 is equal to IR1 plus IR2. That is how we write the expression for the voltages using KVL. Okay, go back and listen for clarity. Then you will know. Next we will take for the loop, for the node, for a junction. If you consider this junction where current 3A is entering and current I is also entering, whereas 2A is exiting from the loop N or the node N. Sorry, it is not loop, it is a junction or node N. So according to KCL, Kirchhoff's current law, sum of currents entering is equal to sum of currents leaving. That is 3A plus I is equal to 2A. 3A is amps. 3 amps plus I is equal to 2 amps. So what will be I then? I is nothing but 2 minus 3. I is here. So 3 has to go that side. So 2 minus 3 is going to be equal to minus 1 amps. So current I is equal to minus 1 amp. So we need to use KCL whenever we need to find current in particular branch, considering the KCL at a node. Okay, next we will see circuit analysis using Kirchhoff's laws with all the sign conventions that we talked about, and also KCL at a node. We can analyze this particular circuit. Now this particular circuit has 2 loops. In the first loop it has EMF V, resistor R1 and resistor R2. In the second loop it has resistor R2 and resistor R3. Okay, this loop current, it is up to you to decide which way you want to take. You can take it like this or in the opposite direction also if you wish, but you should follow sign conventions. Even this also, if you wish to take opposite direction you can take, but you have to follow sign conventions that we talked about earlier. So now in this case it is considered like this, and also this one like this. And first of all, because of the main source, you will consider the conventional direction of flow from positive to negative, remember? So when the current is flowing from the voltage source from positive, I1 flows here, and at the junction it divides. How does it divide? It divides through this branch and also through this branch because they are parallel. So when the current is dividing, we have to call it by a different name, I2. So when I1 is coming up till here, it gets divided. You should think of this as a similar to the pipe, water pipe. When the main pipe is coming and you have 2 other pipes connected to it, water gets divided, isn't it? Same way current also gets divided. So you call the main current as I1 and the divided current in one of the pipe is I2. So the current is also I2. Rest of it flows here. So what is rest? Main current minus the other current. So I1 minus I2 flows in the other loop. That's how you are supposed to write the currents in the branches. So we essentially have first one branch, second branch, third branch. So when we have to find the branch currents, it will be you have to find I1, I2 and I1 minus I2. How to find these branch currents? Using KVL. So you can apply KVL to this loop. Okay, the loop current direction is like this. So if the loop current direction as well as the conventional current direction is the same, then IR drops are going to be positive. And if it is same as the EMF rise, then it's also going to be positive. So in our case, this is also going to be positive, V, and these is also going to be positive. So V is equal to I1R1 plus I2R2. That is our first equation. For the loop 2, if you see, loop current direction is like this, and the conventional current direction for R3 is same as loop current. So this will be positive. I1 minus I2 into R3 is positive, and the loop current goes like this. It is opposite to the conventional current which is flowing through R2. So this drop is going to be negative. I2 R2 will be negative. So how to write? And there are no EMFs at all. So 0 is equal to I1 R2 into R3, this is positive, minus I2 R2. Okay, then this can be expanded, I1 R3 minus I2 R3. So I2 terms, two of them are there. So you write I1 R3 minus of I2 into R2 plus R3. This will become your second equation. First equation is here in terms of I1 and I2. Second equation is here in terms of I1 and I2. So two unknowns, two equations, two simultaneous equations. If you solve them, you will get the value for I1 and I2, because voltage resistance values will be given. You have to find branch currents. So using these two equations, equation 1 and equation 2, you can find currents I1 and I2. Okay, so this is how you solve when two loops are there. We'll take an example on similar circuit what we discussed just now with the values. So we have voltage value as 15, resistance value as 10, and the resistance, this R2 as 5 and this R3 as 20, and loop current is going to be the same, and this is I1 gets divided into I2, remaining I1 minus I2 flows in the third branch. So applying KVL to the first loop, again this is positive in the same direction of the loop current, and both conventional and loop current are same. So this drop I1 into 10 is also positive, and I2 into 5 also is going to be positive. So how to write the KVL equation? Sum of EMFs is equal to sum of IR drops. So 15 is equal to I1 into 10 or 10 I1 plus 5 I2. That is our first equation. Now applying KVL to the second loop. Seeing the second loop, like same as previous explanation, conventional direction of current and the loop current direction is same. So I1 minus I2 into 20 will be positive. As you come towards the second resistor, loop current goes like this, but conventional direction is opposite. So I2 into 5 will be negative. So for the second equation, how do we write? There is no EMF. So 0 is equal to 20 into I1 minus I2 minus 5 I2. So you can simplify this. I2 terms, two of them are there. So it will be minus 25 I2 and plus 20 I1. 0 is equal to 20 I1 minus 25 I2. This will become second equation. You have first equation, second equation in terms of I1 and I2. So you can simplify using simultaneous equations for I1 and I2. When you simplify, you get 75 is equal to 70 I1. So I1 is equal to 75 by 70 equal to 1.07 amps. Substitute I1 value in second equation, then you will get I2. Simplifying, you will get I2 is equal to 0.856 amps. You know I1, you know I2. For the third branch, it is I1 minus I2. Substitute, then you will get 0.214. So this type of problem will be asked for 5 marks. You will be asked to find branch currents. So this is how you go. You write this, analyze this, again and again you should solve the same problem until you understand. Only then you get it. Okay. Next we will take a little more complicated, in the sense we will add EMFs in the second loop also. It is possible you can have many EMFs and many resistors. So in this case, you have to find branch currents for the following circuit having 2 or more voltage sources. So in the first loop, same way we will consider the loop current direction, and this is going to be the second loop current direction. Okay, in the first loop we have one EMF, one resistor, another resistor, another resistor. So 3 resistors or 3 IR drops, 1 EMF. In the second loop we have one EMF and another EMF. So 2 EMFs and 2 resistors. So 2 EMFs and 2 IR drops we are going to have. So how to write the expression using KVL? Just go by the loop current and see if the conventional direction and loop current direction is same, take it as positive, otherwise take it as negative. And here also EMF, if it goes from minus to plus in the direction of loop current, take it as positive, otherwise negative. Okay, so applying KVL to loop 1, this is going to be positive, so E1, all are in the same direction of loop current, so it is going to be all positive. I1 R1 plus I2 R2 plus I3. I1 R1 plus I2 R2, and this current will be same as I1. This is one branch. So same current flows through R3, so this is also going to be I1 R3. That is the first equation. You can take I1 terms together, so I1 into R1 plus R3 plus I2 R2. So you have 2 currents in this equation. Next we will apply KVL to the second loop. When you apply KVL to second loop, we have, this is plus minus. It is going opposite to the, this is opposite to loop current direction, so this will become negative. So minus E2, and when you come down here for other EMF also, this is also plus minus. It is opposite. So this will also be minus E3. But the direction of conventional direction of flow and loop current flow is in the same direction, so this will be positive. I1 minus I2 into R4 is the IR drop for this resistor. That is going to be positive. Coming back here to this resistor, the loop current is in this direction, conventional current is in this direction, so it is opposite. So it will be minus I2 into R2. So that is what we have to write. It is written together. I1 minus I2 into R4 and minus I2 into R2. We have term with I2 here, so we'll put them together. I1 R4 is brought here, minus I2 is taken, R2 plus R4 is written here. So this will become second equation. You have first equation with I1 and I2, second equation also with I1 and I2. Solving these two, you will be able to get the values for branch currents. That's what is written here. Solving simultaneous equations, we can find branch currents I1, I2 and I1 minus I2. We'll take an example for this with values for EMFs. Okay, so this is the circuit diagram. I have taken only one EMF in the one loop 1 and second EMF in the loop 2. Okay, and I am considering the loop 1 current direction like this and loop 2 current direction in the opposite direction from here to here. I told you however you want you can take. So I am taking it in this direction and loop 1 in this direction. Okay, and the first EMF's value is 22 volts, resistor 4 ohms, 2 ohms, 6 ohms, and this is second EMF 44 volts in the second loop. Let us write first KCL at node A. Okay, at node A, what are the currents entering? I am considering current I1 like this, current I2 like this, and both the currents join at node A and it is leaving as I3. So I1 plus I2 is equal to I3. So I1 plus I2 is equal to I3. This is our first equation. Applying KCL at node A, entering current is I1, entering current is I2, leaving current is I3. So I1 plus I2 is equal to I3. So now we will write loop 1 equation for KVL equation for loop 1. So the direction of loop is like this, and conventional direction is also in the same direction. So everything is going to be positive here. So 22 is equal to 4 times I1 plus 2 times I3. That is the equation. But what is I3 from equation 1? I1 plus I2. So substitute here. It will become 4I1 plus 2 times I1 plus I2. So we have I1 terms, 2 of them. To put them together, it will become 6I1 plus 2I2. And they are all multiples of 2. You can divide by 2. Then it will become 11 is equal to 3I1 plus I2. This is our second equation. Now applying KVL to loop 2. And the loop 2 direction flows like this. Okay, so you can see here when the direction of loop current is in this direction and EMF is minus to plus, then this will become positive. And conventional direction is in this direction and loop current is also in this direction, so both are positive. And same here also, both the currents are in the same direction, so both will be positive. IR drops are also positive, EMF is also positive. So how do we write? 44 is equal to 6I2 plus 2I3. That is our next equation for loop 2. But what is I3 from equation 1? It is I1 plus I2. So substitute for I3. 44 is equal to 6I2 plus 2 times I1 plus I2. Expand this and then add 6I2 plus 2I2. That will become 8I2. And then we have 2I1. Again you have all the numbers in multiples of 2, divide throughout by 2, it will become 22 is equal to I1 plus 4I2. This will be our third equation. If you observe second equation and third equation, they are in terms of I1 and I2. Two equations, two unknowns. You can solve them, simultaneous equations, and get values for I1 and I2. And substituting in the first equation, you will get the value for I3. That way you have the first branch current I1, second branch current I2, third branch current I3. All the branch currents you would have found out. So how to solve 2 and 3? Here, second equation is 11 equal to 3I1 plus I2. Third equation is 22 equal to I1 plus 4I2. Whichever you want to eliminate, you can eliminate by appropriately adding that multiple, isn't it? I am trying to eliminate I2. So how to eliminate I2? I have to multiply second equation by 4. So I multiply this one by 4. What happens? This 11 into 4 is 44. 3 into 4 is 12. This will become 4. So 44 equal to 12I1 plus 4I2. Minus, write the third equation as it is and subtract. When you subtract, 44 minus 22 is 22. 12 I1 minus 1 I1 is 11 I1. 4 I2 minus 4 I2 will be cancelled. It will become 0. So we have 22 is equal to 11 I1, or I1 is equal to 22 by 11 or 2 amps. I1 is found as 2 amps. This can be substituted in one of these two equations. So I am trying to substitute in the equation 2. Because I2 is anyway there without any coefficient, so I'll use this. I'll substitute for I1 in equation 2. So 11 is equal to 3 into 2 is I1 plus I2, or 11 is equal to 6 plus I2, or I2 is equal to 11 minus 6, which is equal to 5 amps. I2 is equal to 5 amps. I1 is 2 amps. I2 is equal to 5 amps. We have I3 is equal to I1 plus I2. KCL, applying KCL, remember? So I3 is nothing but adding these two becomes 7 amps. So the branch currents are 2 amps. I1 is 2 amps. I2 is 5 amps. I3 is 7 amps. Okay, this is how you calculate branch currents. These KCL, KVL problems are very important, guys. Please learn them thoroughly. I have given you one more example on similar lines. Same way you have to solve, only numbers are different. Okay, so you can solve this. This is your going to be only one question I have given you. I'll be very happy if you find the answer and send it to me by WhatsApp. I will be asking you. I'll send you a message also. I want all of you to solve this and tell me the answer for I1, I2 and I3. Same, exactly the same way how I showed you just now. Do it. Okay. So I am going to leave you with this quote. You have to plan if you want to achieve anything at all. If you have a goal to achieve, you need to plan first, then prepare thoroughly, and then eventually you perform. Performance is going to be good if you would have planned well and prepared well. Remember, this applies everywhere for everything, including your studies. Okay? Take care. I will see you in the next session. Thank you.